Welcome back, everyone. This is Mr. Bowman. We are going to start working on activity 3.2b in just a moment, but I wanted to highlight for you the goals of this activity. We are going to, not in this order necessarily, calculate and interpret what a residual is, interpret the slope and y-intercept of a regression line, which we've done a little bit of already, construct and interpret residual plots to determine whether a regression model is appropriate, and find the slope and the y-intercept of the least squares regression line from the means and standard deviations of x and y along with the correlation. So let's get started with the last thing first. We are going back to our distance airfare data, and what we have here are the means and the standard deviations for both the distance, the explanatory variable, and the airfare, the response variable. And then we have the correlation coefficient over here on the right-hand side. Well, it turns out that if we write the equation of the line of best fit in slope-intercept form, so y with a hat over it is equal to ax plus b, where a is the slope, b is the y-intercept, x is the explanatory variable, and y hat, a new symbol for most of you, is the predicted y value. If we write the equation like that, the slope can be found using this formula right here. Take the standard deviation of the response variables divided by the standard deviation of the explanatory variables and multiply by the correlation coefficient. Once we know the slope, we can plug in this not very well known but very important fact that every least squares regression line goes through the point x bar, y bar. So if we plug in x bar, y bar, which we already know, x bar is the average for the explanatory variables, y bar is the average for the response variables. If we plug those in, along with the known slope that we just found, we can find the y-intercept, and then we will have our line of best fit. I encourage you to take a moment to actually do that right now. Use this information and find the slope using this formula, r times sy over sx, and the y-intercept then using the other formula, b is equal to y minus ax bar. When you get done with that, you should get the same equation that we got in the last activity for the least squares regression line. So go ahead and pause the video right now and do that. So here's the work required to find the slope and the y-intercept, and as you can see, you get the same slope and y-intercept that we got when we used our calculator to find the least squares regression line. Now you might be asking about remembering these formulas. You do not have to remember those formulas. They are on the formula sheet right here. They are, let me highlight them for you in, let's say, blue. They are this formula right here and that formula right there, right up in front on the first page of the formula sheet. So we've talked about this idea of interpreting the slope already, but we want to do a little practice with this. So what I would like you to do is I would like you to fill in the blanks in this table where you're given distances of 800, 801, 802, 803 miles. Take your calculator, find those corresponding values, and plug those in. So pause the video for a moment and go ahead and do that. I guess I forgot to mention this, but it's important in this case. I rounded off my predicted airfares to the nearest penny because we're talking about the cost in dollars. And what you'll see here is that the predicted cost for an 800-mile flight is $282.47. If you add a mile, that cost goes up by approximately 20 cents. If you add 2 miles, it goes up by another 20 cents. And if you add another mile, it goes up by another 20 cents. And you're probably thinking, well, obviously that's the case. But that is showing you exactly how we interpret the slope in context. Our slope is 0.20 approximately. And so as the explanatory variable, distance, goes up by 1 unit, or 1 mile in this case, the predicted airfare goes up by 20 cents. In this next part of the activity, we want to take another look at the relationship between the explanatory variable, the response variable, and the slope. So we're going to do that in a little bit different way. Here you have the average distance, you have the standard deviation of the distance, you also have the average airfare and the standard deviation of the airfares. What I'd like you to do is pause the video for a moment, more than a moment, and convert all of these distances to standardized values by subtracting the mean distance and dividing by the standard deviation. Then I would like you to find the corresponding airfares, or the predicted airfares for those particular distances, and convert those to standardized values by dividing by, or subtracting the mean airfare and dividing by the standard deviation of the airfares. This may take you a few minutes. Pause the video and do that. So when everything's said and done with this table, it should look about like this. And what I want you to notice here is the following, is that these distances, when converted to z-scores, convert to z-scores that are nice whole numbers, -2, or integers, excuse me, -2, -1, 0, 1, and 2. So basically that's telling us that those how many standard deviations above or below the mean distance those values are. Now if you look at the corresponding predicted airfares, there might not seem to be much of a pattern there, but when we look at their corresponding z-scores, -1.75, -0.87, 0, 0.87, and 1.75. If you take a close look at that, what you will see is that as the distance is going up by 1 standard deviation, the predicted airfare is going up by r times 1 standard deviation. Another way of looking at that is basically saying, as the explanatory variable increases by 1 standard deviation, the response variable is predicted to change by r standard deviations. And in our case, r is 0.87. So as x went up by 1 standard deviation, or as distance went up by 1 standard deviation, r went up by 0.87 standard deviations. So that's another relationship between the explanatory variable and the response variable when you look at the least squares regression line. All right, we are skipping around a little bit here. So the next thing I want you to take a look at are these two data sets in this activity. And what I'd like you to do is I would like you to use your calculator and put those data sets in lists and find the correlation for both of those two data sets. Find the value of r. Then I want you to take a minute and I want you to answer this question right here. Which of the two sets of data is it appropriate to fit a line to? And I'd like you to think about how you would justify that. So go ahead and pause your video and do that now. So before we answer which question or which set of data it's appropriate to fit a line to, hopefully you looked at the scatter plots, and hopefully in those scatter plots you saw that the first set of data, the relationship was fairly linear, and in the second set of data it was clearly curved. And even though those two sets of data had exactly the same correlation coefficient, and they had exactly the same lines of best fit, it is entirely inappropriate to fit a set of data or a line of best fit to set 2. So the next thing I want to talk about is how another method that you can use to help you distinguish between whether or not you have a linear set of data or a curved set of data. If you recall, in the previous activity, we talked about the least squares regression line. And the least squares regression line is the line that fits the data such that the sum of these vertical squared deviations from the line of best fit is a minimum. Well, those deviations are called residuals, and a residual, by definition, is equal to the actual y value minus the predicted y value. So y minus y hat, actual minus predicted. That is something that is not on the formula sheet, and you will have to commit to memory. Well, there's something called a residual plot. So right below these graphs right here are the residual plots. And I'm going to explain what they are, what they show you, and how to make one on the calculator. So if we were to go look at the curved data, you will see this point right here falls almost entirely on the line of best fit, which means the difference between the actual y value and the predicted y value is virtually 0, or the residual is 0. Well, if you go straight down to this residual plot down here, you will see that that point lies on a residual value of approximately 0. Whereas this point right here, kind of in the middle of that curve, has a very large, relatively speaking, positive residual. The actual y value is greater than the predicted y value. And if we go straight down, you will see that that point is plotted above the line y equals 0 on the residual plot. And we can do this for all the points. This very point on the right-hand side has a negative residual, and if we go straight down, you will see that that point is below the line y is equal to 0 on this residual plot. So what is a residual plot? It is a plot of either the explanatory variable on one axis or the response variable, you could use either, versus the value of the residual. And effectively what it does, especially if you use the explanatory variable on the horizontal axis, is it magnifies any patterns that you have in the data. And for a line to be appropriate to fit a set of data, we don't want to see any pattern. If you look at the residual plot for data set 1, there's really no pattern to this. Whereas if you look at it for data set 2, it clearly magnifies that curvature. So when you look at a scatter plot, you should be looking for a linear association before you try to fit a line to it. If you need to take a closer look at it, which very often you do, you can make a residual plot. If you see a pattern in the residual plot, it's not appropriate to fit a line to the data. So the next thing I'm going to do is we're going to take this data here, and I'm going to show you how to make a residual plot on your calculator. If you haven't already done so, what I would like you to do is to enter the data from set 2 into two lists in your calculator, make a scatter plot, and then find a line of best fit, and then I will show you how to make a residual plot. All right, as you can see, I found the line of best fit here. As you already saw, the slope is 1/2, the y-intercept is 3, and the value of r is approximately 0.82. So I am going to make a scatter plot with this data and the line of best fit, just so you can see that it's that same data. And I have that there, but I think I forgot to turn the plot on and use the new window. So zoom stat number 9. There's our curved data with our line. We know it's not appropriate to fit a line to this data. In the process of finding the line of best fit, the calculator must find the residuals. So it does that, and it stores that in a list called resid. Even though it's obvious in this case, it's not in all cases. So it's always a good idea. You should always look at the data. And when you're finding a line of best fit, you should start with a scatter plot. And then if you need to, take a look at the residual plot as well. So here's what you do after you've found the line of best fit and you've looked at the scatter plot. You're going to go over and you're going to change the plot that you have. And my explanatory variable is in list 5. And what I'm going to do is change my Y list to a list called resid. Now, you can't do this until you find a line of best fit for the set of data that you're working with. Otherwise, it's just not going to work. So once you put the cursor on Y list, you can hit second and the stat button, and one of the lists that comes up is the list resid. If you select that, now what you're doing is you're making another scatter plot with the explanatory variable on the x-axis and the residuals on the y-axis, similar to the one that I showed you a few moments ago. You are going to have to change the scale here, or the window, so go ahead and hit zoom stat number 9, and that's our residual plot. It's just a magnification of what we saw on the scatter plot. I would like to show you also that you will see a pattern if instead of using the explanatory variable, you use the response variable, which I happen to have in list 6. So we're going to do the same thing. Response variable on the horizontal axis, residuals on the vertical axis, zoom 9, and you see a different pattern here, but you still see a pattern. And any pattern in a residual plot indicates that it's not appropriate to fit a line to the data. So once again, we find ourselves at the end of this activity with several conclusions that you should have made based on this activity. And what I would like you to do is I would like you to, before you end the video, pause it, read through each of these conclusions, and take note of them. And if you have any questions about them whatsoever, make sure that you ask your teacher in class.